I think we can get started. Okay, well, we're very happy today to have Patricio. He's going to talk a bit about an effective description of the Morbiid fractional quantum Hall state from the Nappi-Witten supersymmetry. So please, Patricio, please take it away.
Thank you. Thank you, also. Thank you very much for the opportunity to talk about my research here. In this opportunity, I'm going to talk about an article that I wrote in collaboration with Gian Domenico Palumbo. Actually, two articles that are here, which are we can think of first and second part of a project, and it's about the Nappi-Witten supersymmetry and how it can be related to the Morbiid in the fractional quantum Hall state. So. The fractional quantum Hall state is one of the most important problems in condensed matter physics, and the classical setup is really simple. So, if in a two-dimensional plane, if there is a current of electrons and a magnetic field that's perpendicular to the plane, then there is an electric field that appears that's both perpendicular to the magnetic field and the current. And I took this picture from the nice review by David Tong. So when the temperature is really low and the magnetic field is strong, there appear plateaus in the conductance that were first discovered to be integer, and that was the discovery by von Klitzing in the 80s, and later. It was discovered that there could be also fractional values of the conductance in terms of this von Klitzing constant is square over 2 pi h bar. So here there is a picture to show this result that the peaks that appear, the plateaus for the resistance in this case. That's the inverse of the resistivity. In the low energy regime, fractional quantum Hall states can be described by means of Chern-Simons theory. Actually, one can easily see that the Hall law, this one, that the typical Hall law that we all know, can be obtained as the field equation of a Chern-Simons action. So if one varies this action, that is the Chern-Simons action with respect to A, one obtains the Hall law automatically. And nu is quantized, so is restricted to take integer values. Now, if one wants to describe also fractional values for nu, as in the fractional quantum Hall effect, then what one can do is to introduce an emergent field A and consider an action of this form. When here I'm considering like this differential form, so this is. This Chern-Simons action in terms of small a has the same form as this one. I'm just like trying to not use so much notation. So if one integrates out this field small e, one can recover a Chern-Simons action like before, but with a fractional value for nu. So it's been shown that the quantum Hall effect can be described in terms of Newton-Cartan geometry when the fractional quantum Hall effect happens occurs in a curved surface, in a curved space, let's say. And the ingredients that one has to add in that case are the spatial metric and the clock form that together form what is usually known as the Newton-Cartan structure. So instead of a relativistic metric, one has a spatial metric and a clock form, and there is also a spin connection that defines the curvature of the geometry. So in that case, it's been shown that one has to generalize the action that we had before to include also a Chern-Simons term in the spin connection, which accounts for the gravitational anomaly, and the Venn term that couples the electromagnetic field with the spin connection. And here the coefficients in the action have a physical meaning. Nu is the fractional filling as before. C is the central charge, the chiral central charge, and S is the average orbital spin. So Laughlin states are characterized by fractional values of nu of this form, where P is an integer and C equal 1, which means that in this case, the boundary modes, the edge modes of the system are chiral and can be described by means of chiral boson action. Then other states appear in the fractional quantum Hall effect. The one that we're interested here is the Mouride state, which it's a candidate to describe non-abelian anions. And in this case, the filling factor is given by 1/2, and the central charge is 3/2, which means, unlike before, it's not only a chiral boson, but this time we have also a Majorana mode together with the chiral boson. So in that case, the boundary theory, the edge theory, can be written in this form. So the first term here is the chiral boson, and we have a Majorana mode. I have a typo here. This should be a BF, so the velocity, fermionic velocity, and this one is the bosonic velocity. So it's been recently shown, and this has been a motivation for us to do our work, that this action admits a supersymmetry, n equal 1 supersymmetry, in the limit of B boson equal B fermion. So in general, the supersymmetry is broken, but there is a special case where one can find a supersymmetry in the edge theory of the Mouride state. So there are also other modes that appear in the fractional quantum Hall effect that are not captured by this Chern-Simons picture. For example, the GMP mode, the spin 2 GMP mode, that's also being termed magnetoroton, which seems to be a massive graviton. And further modes, some of them have been also conjectured to be supersymmetric partners of the GMP mode. So these two results separately were sort of the motivation for us to consider also supersymmetry in our case. I will show you first the bosonic description of quantum Hall states that we obtained, and later how we extended it to supersymmetry, to include supersymmetry. So as I told you before, the fractional quantum Hall effect admits a description in terms of Newton-Cartan geometry, which is a particular type of geometry that can be understood as the non-relativistic limit of Riemannian geometry. So one can write Newton equations in a covariant way, and they can be thought as a limit, non-relativistic limit of Einstein equation in this sense. So yes.
So, I'm not familiar at all with this Bargmann-Newton-Hooke algebra. Is this related to the Galilean algebra? Is it embedded in it? Or just some completely different beast?
Well, it's kind of the same. So let me see here. Maybe I'm missing some commutation here. Yeah, it's possible. But the point is that the Galilean algebra and the Bargmann algebra differ just by a central term. So one can show there is a central extension of the Bargmann algebra, which appears in the commutator of translations and boosts, Galilean boosts. But okay, maybe I have a mistake here because I don't see it. So this should be the Galilean Newton-Hooke algebra without the central extension. So sorry, you're right. This is the Galilean algebra in the case the cosmological constant lambda is 0. And when lambda is on, this is called the Newton-Hooke algebra. Now you can add a central term in the commutator of Galilean boost and translation that's known as the mass generator, and that's the Bargmann algebra. And there is also an extension, Newton-Hooke extension, including this central term that could be, it's been called sometimes extended Newton-Hooke algebra. So here, this is the Galilean one. This is not Bargmann, actually.
Okay, great, thanks.
Yeah, thanks for the correction. So this type of symmetry, so the Newton-Cartan equations, for example, for to describe the gravitational field in the Newtonian limit, can be obtained by gauging the Bargmann algebra in the same way as general relativity can be obtained from the gauging of the Poincare symmetry. And in 2 + 1 dimensions, there has been a lot of research and a lot of examples of non-relativistic gravity theories have been constructed by gauging different types of non-relativistic symmetries. In this case, is the Bargmann symmetry, for example, here. This is the right action for the Bargmann symmetry, because here we have this M field associated to the extra generator that I missed in this.
Sorry, can I ask a question?
Yes.
So, so P is the translation generator?
Mm-hmm.
What is
Right.
G? What is G then?
G is the generator of Galilean boosts.
Okay.
Yes. So there are still boosts in this symmetry. That's why it's still covariant. So there's still something that survives from the relativistic boosts when you take the limit of speed of light going to infinity in the Poincare symmetry.
Okay.
Yes. So yeah, and J here, JAB is the generator of rotations. Yes. So people have constructed this type of Chern-Simons actions for many non-relativistic symmetries, not only Bargmann or Newton-Hooke, also extensions and supersymmetric extensions and hydrospin extensions, and they have terms that are really close to the effective action for the fractional quantum Hall effect. So that's why, looking at this, one could think maybe there is some symmetry, non-relativistic symmetry, that one could gauge and obtain something like the action that I showed you before to describe the fractional quantum Hall states. So, and this is the question that let's say we wanted to address in our work. If there is some symmetry that one could gauge to obtain geometric models to describe the quantum Hall, fractional quantum Hall effect. So there is also an extension of the Poincare symmetry, which is called Maxwell algebra, which I will just briefly comment. So the only difference with the Poincare symmetry is that the translations do not commute. And it's been shown that this type of algebra that include an extra generator, an antisymmetric tensor Z here, describe particle systems in the presence of a constant electromagnetic field. So this type of symmetry is well suited to describe, for example, the quantum Hall effect. At least that's what we thought. And this symmetry, in the same way as Poincare or Bargmann, has also been used extensively in the high energy community to construct higher spin gravity theories or supergravity theories in 2 + 1 dimensions and higher dimensions. This algebra accounts for magnetic translations in the same way as it happens in the quantum Hall effect. So if we want to use some sort of symmetry like the ones that I showed you before, but we would like, if we want to construct a theory that captures the physics of the quantum Hall effect, it's likely I mean, it's possible that one should include a commutator of this form, like in the Maxwell symmetry, and actually that's what we did. So the outline of the talk, first I will show you the extended Nappi-Witten symmetry and how one can use this algebra, engage it to obtain a geometric model for Laughlin states. Then in the second part, I will show you the supersymmetric extension, how this one can be used to obtain the Moore-Reed, the edge theory. And then how one can break the supersymmetry by means of a goldstino to obtain, let's say, the full the full description, at least at the boundary. So the Nappi-Witten symmetry is given by these two commutators, really simple. So here's where we use this ingredient of the Maxwell symmetry. So we want somehow to include magnetic translations. We don't want translations to commute. And then since the symmetry we want to use accounts only for rotations of the plane and translations in the plane, the other natural commutator is this one. And one could associate to J the spin connection, scalar spin connection. This spatial translation should be associated to some spatial Zweibein. And we are going to use this extra generator T to accommodate the electromagnetic field. But there's still another field that we should have in this effective description, which is the emerging gauge field that I showed you before, small a. So naively, one could try to add a U1 generator and just plug this here. But this will not work as I will show you now. So one can show that this symmetry admits a bilinear invariant form. And one can compute a Chern-Simons action that's automatically invariant under this symmetry, and it's given by this expression. So obviously, we, as Y is totally decoupled, we cannot get a term of this form coupling the electromagnetic, the E1 field with the emergent field small a, which we should integrate out to obtain these fractional values for the conductance. So the trick that we used was to shift the spin connection in this form where beta is some arbitrary parameter to create a new connection. And by doing that, one obtains an action that has all the terms that one would like to consider. So if one imposes the constraint that appears by varying the action with respect to the Zweibein and plugs it back into the action, and redefines the constant appearing in the bilinear form, invariant bilinear form like this, one obtains this simple action that has all the terms that are necessary to reproduce what we want. So, but the shifting in omega that we did before can be reinterpreted as a shift in the U1 generator that we introduced by hand. If one does that, then one deforms somehow the original Nappi-Witten symmetry, which is given by these two commutators, by adding an extra one. And this is what we term the extended Nappi-Witten symmetry. So one can show that by computing the most general bilinear invariant form of this algebra and constructing the Chern-Simons theory, one obtains automatically this action that I'm showing you here. And then by identifying the parameters in the invariant bilinear form, which are arbitrary in this way, one can recover the action that has been used in the literature to describe the Laughlin states in the fractional quantum Hall effect.
So I'm confused. It sounded like on the previous slide, it looked like you just introduced what you wanted by a field redefinition.
Yes, that's right.
But field redefinitions don't change physics. So why it seems like you're getting a free lunch here.
Yeah, well, somehow at the end one is changing the symmetry in this way, because of course one could think that this connection is the same as before with the shift, but physically anyway what I'm going to interpret as the spin connection of the system, what defines the geometry, is only this one and not that one. So if I want to go back to a connection that looks like that, where omega goes only along what I will interpret as the angular momentum, I need to define a new generator that, let's say, absorbs all this redefinition. And this changes the algebra. So I could have just started with this symmetry and not with the previous one. And then if I compute the invariant linear form and I construct the Chern-Simons action, then I recover this. Yes, I could have started just with this one, for example. And then this would be the result. I don't know if this answers your question, because it's, of course, it would be the same theory and just a field definition if I kept the role of the generators of the symmetry in the same way, but I'm not doing that. I'm changing the algebra.
So are you doing both the field redefinition and the change of the algebra?
Well, if I modify the algebra, I don't need to do at the end the field redefinition. That's the point. I can absorb these redefinitions in a different algebra where now something else is representing the angular momentum.
Sorry, just a quick question.
Yes.
If your Z is a linear combination of your old generators, how is this a new algebra? Wouldn't that just be the old algebra written in a different basis?
You said C? Do you mean this C?
No, it's the capital Z.
Z.
Y plus beta J.
Yes. Mm-hmm.
So the extended Nappi-Witten algebra is what you get from the old Nappi-Witten algebra just by defining Z this way, or is it?
Yes, that's right.
So it's still the same algebra, no, but just written in a different basis.
Yeah, but what you call angular momentum, so the ingredients in the connection that you use to construct a geometry is different. So
right.
Omega and E here define my geometry, and before it was a different object that I. And
right.
Yes.
But that, I guess, that should correlate with the fact that it's this new algebra, well, which is the old algebra in a different basis. It results in a field redefinition.
Yes.
Okay. Thanks.
Yeah, actually, this algebra I can embed it into. This is something I didn't show, but there is an extension of this Maxwell algebra that I showed before. That has these commutators. So one can show that. Imagine if you want to have a full Newton-Cartan geometry, where you also have, for example, a Hamiltonian generator, and also Galilean boosts that are not present here. One should enlarge the algebra, and this symmetry should be like a subalgebra of something larger, where you would have also temporal translations and Galilean boosts. So there is an extension of the Maxwell algebra that admits these commutators, and this extended Witten algebra is a subalgebra of this larger, let's say, extended Newton-Cartan symmetry. But this doesn't happen with the other one. If I stay just with this one, then I cannot find an embedding in a full Newton-Cartan symmetry that comes from the Maxwell algebra. That's at the end what I was interested in. But I wanted to skip that part because I thought it would be maybe like losing the point. I just wanted to show you that there is a symmetry that you can gauge, and you can recover a Chern-Simons action with 4 independent parameters with these terms that are the ones that one needs. And upon integrating out the hydrodynamical field small a, one can, by means of this redefinition of the constants, reobtain what is known to be the effective theory for the Laflin states.
I see. Thank you.
Okay.
So the last equation is there are 3 parameters only, and you had 4 in the beginning. How many do you lose one? Did you lose one parameter? You said you can parameterize the action in terms of 4 parameters. I'm just trying to count if there are still 4.
Well, actually, I have even more. Yeah, at the end, this is something. At the end, we had too many constants, so we set, for example, mu1 to 0. There was some freedom here. I could have set also beta to 1 and choose mu3 in a different way. So at the end, this beta is not really necessary, for example. We used it in this case, but when I will show you the supersymmetric extension, then I will take the other way. So I could have found a different redefinition here, where I don't use beta, for example, and here I didn't use mu. So at the end, I got even more than what I needed, the amount of independent parameters. I don't know if this answers your question. Okay, I will continue then. So later, what we wanted to know if is this Nappi-Witten Chern-Simons theory can describe more states or only, I mean, beyond Laughlin. And then we started looking at the Moore-Reed state, where we knew that the boundary theory also needs to include a fermion, a Majorana fermion. So at least if we want to reproduce the limit of the boundary theory that's supersymmetric, considering a supersymmetric extension of the algebra that we had before looked like a natural next step. So the way to do that is first noticing that this Nappi-Witten symmetry can be understood as a non-relativistic limit of the Lorentz symmetry. So if one starts with the Lorentz symmetry, SO21, and one adds now an abelian generator, it's not the same as before, it's just some new abelian generator to the Lorentz symmetry. So we have these commutators that are just the Lorentz algebra in 2+1 dimensions that can be split into temporal and spatial components, and one adds something else that commutes with everything. One can use this redefinition of generators, and in the limit epsilon going to 0, one recovers Nappi-Witten symmetry. So in some sense, one can think the Nappi-Witten algebra as the non-relativistic limit of the Lorentz algebra. And the supersymmetric extension of the Lorentz symmetry is known. So one can generalize the rescaling that I showed you before now to include the fermion generator, the supercharges. And one can take this relativistic commutator and anti-commutator into these ones, where we get now this central term that appeared for the translations in the anti-commutator of the Qs. And if one introduces this new Z generator in exactly the same way as we did before, one can define the supersymmetric extension of the extended Nappi-Witten algebra that I showed you at the beginning. So in this case, maybe this is related to one of the questions that I got. In this case, as we realized before that we had some freedom, we could set one of these constants that we had as to 1, and we still had the freedom to accumulate everything. Here we decided to just forget about beta. So the invariant linear form for this super algebra can be obtained directly from the previous one, just by adding this bracket for the Fermionic generator. And then one can automatically construct a Chern-Simons action. So the connection is the same bosonic connection that I showed you before, but we just add some fermionic field that goes along the supersymmetric generators. One can compute the curvature, and it's the same as in the previous case, just the field strength of the electromagnetic field picks up a contribution. And there is also the covariant derivative of the fermion field that takes this form in terms of both omega and A. Then the Chern-Simons action for this super algebra takes this form, which is the same bosonic Lagrangian that we had before, plus this term. That is, it resembles, like in the relativistic case, what's the Rarita-Schwinger field. So one can try now to study the edge theory by using the Chern-Simons Wess-Zumino-Witten correspondence, given a Chern-Simons action and invariant under some symmetry that admits a non-degenerate invariant bilinear form. One can use the field equations of the Chern-Simons theory to express the connection, the spatial connection in this way. So if one considers the boundary condition AT equals A phi with some proportionality constant V, which is usually what people do in three-dimensional gravity to construct boundary theories, one obtains a Wess-Zumino-Witten model associated to this supersymmetry that I showed you before. So if one wants to write this explicitly, in terms of fields that go along these generators of the Nappi-Witten supersymmetry, what one can do is to realize that all the components, let's say the terms that appear in this action have the form of the Majorana form. Just so this prime here is derivative with respect to phi, and this plus here is just the derivative with respect to x plus, which is defined in this way in terms of t and phi. And this g tilde is the bulk extension of the group element G that lives in the boundary. So all the terms here have this form. So if one solves the Majorana equation, one can find the explicit form of the Wess-Zumino-Witten term. So the solution in this case can be found, and is written in terms of two zero forms theta and phi, and also a vector, Nappi-Witten vector, we can call it a sigma, and a spinor field chi beta. So this is somehow a long computation that I don't want to show you, but you can believe me that if one replaces these components of the Majorana form back in the Wess-Zumino-Witten action, one obtains up after solving a constraint and redefining the fermion in this way, where here beta, okay, maybe here I should have added more detail, but beta is just an arbitrary function of x minus that appears when solving one of the constraints that one obtains. But one can reduce the Wess-Zumino-Witten to this expression, which is the sum of a chiral boson and a chiral Majorana fermion, both with the same velocity, which is given in this case by b. So by computing the Wess-Zumino-Witten model associated to this super Nappi-Witten algebra, one can obtain at the boundary the same supersymmetric limit, let's say, that was obtained before in the literature for the Morley state. And of course, when these velocities are not the same, then one breaks supersymmetry, and one is, let's say, out of this sector. But at least for the supersymmetric sector, one can obtain the boundary or edge action from this super algebra. So are there questions up to this point?
So the GMP mode is not incorporated here?
No. This is not. Yeah, that's something that we would like to address at some point, but we would need to add more field content to the theory to do that. Yeah, it wouldn't be a Chern-Simons action. It should be some non-topological term that should be added to the theory. But I will show you here at least how to make dynamical the fermion field in this. So in this supersymmetric picture that maybe you have in mind, the GMP mode has a super partner which is interpreted as a gravitino. So the gravitino we have here is not the super partner of we don't have a second metric that could be the bosonic partner of the fermionic field we have here. So in that sense, this is an incomplete description. One should extend even further this construction to account for that. This is what we found as the minimal construction, let's say, gauge algebra that after constructing the Chern-Simons action could reproduce the chiral boson and the chiral Majorana mode at the boundary. Yes. So if we want to analyze the broken supersymmetric phase of the system, we need to break the supersymmetry. So here, so this is like analog to what happens in supergravity, where if one adds a mass to the gravitino, one breaks the supersymmetry. So In this case, we will use a method that was developed by Gian Domenico, where he came up with a gravitational action that can be used a goldstino action that can be used to give mass to a spin 3/2 field. So the action has this form where eta here is the gravitino, is a neutral fermion. And we use here to construct the action a matrix that we term gamma hat that is constructed out of gamma 0 and the clock form of the Newton-Cartan geometry that we are considering. So tau is not a gauge field here. We consider it as a fixed non-dynamical clock form. But of course, if we want to embed this, as I told you before, in a full Newton-Cartan geometry, then this tau could be dynamical, and there would be also a gauge generator associated to it. But we don't need that. We don't need that here, at least. So this action is metric independent. It doesn't introduce more content to the theory, and it can be shown to be a boundary term. So if we fix the gauge, let's say, since this non-dynamical clock form is fixed, one could just choose it to be choose tau to be dt, and then if we use the boundary condition that the goldstino matches the boundary value of the solution of the Majorana form that I showed you before, we can obtain this contribution of this action at the boundary, which the effect that it has is to precisely modify the fermion velocity of the action that I showed before here. So in this sense, this action also breaks supersymmetry at the boundary, not only in the bulk. So the method to give mass to the spin 3/2 field is to introduce this shift in the covariant derivative of eta. And then one can see from the previous action that this generates the following mass term for the spin 3/2 field. So in the limit when m is large, we can neglect like the coupling that we introduced between eta and psi. So we are only left with some sort of Rarita-Schwinger like equation for psi. And it's been shown in different papers that even though the Rarita-Schwinger field in 2 + 1 dimension doesn't have propagating degrees of freedom when one adds the mass, there is 1 degree of freedom associated to the Rarita-Schwinger field that obeys the Dirac equation. So if one integrates out the massive Rarita-Schwinger field in the action, this produces a Chern-Simons term in the same way as it happens with the Dirac field. So if one does that in this case, one generates a Chern-Simons term with the connection that was used in the construction of the covariant derivative of this action. I mean the previous one, the kinetic term for the spin 3/2 field. So if one adds this term up to the original action that we had, then one obtains a new combination of the terms that we were interested in that again can be connected to the constants in the invariant tensor of the extended supersymmetric Nappi-Witten symmetry in this way. And by picking up the values that are known to describe the Moore state, we can match the model. And of course, if one can vary the action with respect to A0, with respect to AI, to obtain the form of the electric Hall density and the density current, and one can vary also the action with respect to the spin connection to obtain the spin current in this way, which is related to the Hall viscosity. So this mapping allows us to describe the physical properties of the Moore-Reed state in terms of the arbitrary constants that appear in the invariant tensor of the supersymmetry algebra. And by means of this goldstino action, we managed to break the supersymmetry both in the bulk and at the boundary, which makes the edge Majorana mode to have a different velocity than the chiral boson mode. So with this I'm finishing. So we have constructed an extension of the Nappi-Witten algebra that allows to construct a geometric model for the fractional quantum Hall effect. Also, we showed that it admits a supersymmetric extension. And by adding this supersymmetric generator to the connection, one can construct a spin-free half field that is an expected excitation in the Moore-Reed state, even though one should add something extra to this theory to make it be the partner of some GMP mode. But at least the Wess-Zumino-Witten action induced at the boundary is a supersymmetric CFT, which includes the chiral boson and the chiral Majorana fermion that are expected to occur in the edge theory of the Moore-Reed state. And by introducing a suitable goldstino action that breaks the supersymmetry, the spin-free half field becomes massive. And at the boundary, we can also break the supersymmetry and make the velocities of the chiral modes different. And finally, we integrated out the Fermionic field to find a purely bosonic theory that encodes the topological response of the Moore-Reed state. And the possible generalizations of this work that we have in mind is the inclusion of higher spin fields, which related to a question that I got. Something I would like to do is to try to accommodate a second metric and maybe make it massive by means of some similar procedure. And also to go to even higher spin constructions. So thanks.
Questions? Any questions on Zoom either?
Yeah, so what's the scale? So there's some scale in the theory which is associated to the mass of the GMP mode. What's the scale of this spontaneous breaking of supersymmetry relative to that scale?
Oh, yeah. Yeah, that's an interesting question. Yeah, I don't know what this scale could be. Maybe it could be interpreted as some of the parameters that we have there, but I haven't thought about that.
I mean, is there experimental data on the relative velocity of the fermionic and bosonic edge modes?
Yeah, that could be interesting. Actually, well, the parameter that makes this velocity different is we found different ways to incorporate it. So the simplest one we found was to include it as a global term here in the action. But also it could be interpreted as some parameter that including the boundary. For example, if I had modified the boundary condition to put this sigma here, I would also get the same result, but just with some parameters squared here. So also another way we found to obtain the same result was to use this shift in this. So after implementing this shift, we can associate this boundary value of the goldstino as the boundary value that appears in the spin-free half field. So one could try to reduce at the end this action to the boundary. So if this action is reduced to the boundary, then we would have the mass here appearing explicitly. So yeah, this is something that I didn't mention, but instead of doing this construction, if I had implemented the shift first and then to try to obtain, to reduce the the theory to the boundary after introducing the mass term, then it would be this, the term that introduces the mass, the one that will be reduced to this quantity. And the reason is because this psi at the boundary is given by a phase times this fermion k that we later rescale to psi. So the phase goes away when we replace it in this mass term. But this rescaling here that is related to V and also to the mass later would be something that would at the end fix this sigma. So also in that case, we should find we should maybe consider some specific value of beta here. That's a constant that, sorry, it's a function, arbitrary function that we introduce in the construction. So I don't know if in that way one could find some scale like the one you said, but it's a really interesting point.
Okay, thanks.
Sorry, can I ask a question?
Mm-hmm.
So in your theory, many consider the spin field 3/2. So can you say more about like the generalization of like to the spin higher than 3/2 cases?
You mean to go beyond
Yeah.
spin 3/2?
Yeah.
Yeah, this is something that it's like a work in progress now. So the idea that we have to include the higher spin modes is to construct also higher spin extensions of this algebra. And this can also be done using a similar method to the one that I showed you here. So in the same way as the Poincaré symmetry in 2+1 dimensions or the Lorentz symmetry admits higher spin extensions, and Chern-Simons theory for these higher spin symmetries have been constructed, one could also define a higher spin extension of this algebra by including, I don't know, some generator JAV. Then there is also a contraction of this form that allows you to define a higher spin extension, bosonic, of this symmetry. And we haven't tried yet, but for sure there should be a way to incorporate also fermionic fields, let's say spin 5/2. There are in 2+1 dimensions theories of what's called not supersymmetry but hypersymmetry, which introduces a spin 5/2 field by means of some hypersymmetric extension of the Poincaré symmetry. And there are also non-relativistic limits of those algebras, and one could, I'm sure, even though we haven't tried, it's possible to define a hypersymmetric extension of this symmetry. So in this way, one could go further and include higher spin fields in this Chern-Simons action. Mm-hmm. Now, the relation of this with what's known in the literature and how to make them dynamical, because this would be, of course, purely topological all the time, that's something that I don't know.
Thank you.
Okay, if there are no more questions, maybe we can thank the speaker one last time.
Thank you.